In this video, we're going to talk about probability, and I'll introduce some of these vocab words like the intersection, union, conditional probability, independent events, and mutually exclusive events. First of all, you've probably seen like a Venn diagram or things like that represented for probability, and let me just explain a little bit about where that comes from. So basically, let's say we have event A, which is going to college. Let's say event A is the probability that you find a randomly selected person and that they have a college degree. Well, one way to think about that just visually is imagine if you have like a 1 foot by 1 foot dartboard, and you're basically trying to figure out what's the likelihood of somebody throwing a dart at random in that 1 foot by 1 foot and it landing somewhere in this circle. Well, the total area here is just 1. And so the likelihood of it randomly landing somewhere inside that circle is just the probability of this event. So we're going to call this circle event A. And let's say the probability of somebody going to college is 0.5. So notationally, if event A is going to college, then the notation we'd use is that P of A is 0.5. That means that there's a 50% chance that somebody, a randomly selected person, has gone to college. That means that the area of this circle should be 0.5, 0.5 out of the total area of 1. And so again, the chances of randomly landing somewhere in there is 0.5. Again, that's just a visual representation of that. And that helps when it comes to thinking about two events at once, for instance. So let's say there's a totally different event, which is you find a randomly selected person, and that person voted in the most recent election. So it's like, all right, the probability of that happening, let's say, is 0.6. So if event B is having voted and the probability of it, P of B, is 0.6, 0.6, that means that the area of event B is 0.6. All right, now notice that they might have a little bit of an overlap here, meaning if you throw a dart randomly in this 1 foot by 1 foot thing, there's a chance that it lands somewhere in this overlap region. And in that case, it basically is a part of event A, and it's also a part of event B. So that's basically like if you randomly select a person and it turns out that they have a college degree and they voted, then they're technically a part of that overlap. So let's say that area of that overlap, let's say we know that. And let's say we know that to be 0.3. Meaning this means that 30% of people out of everybody both have a college degree and voted. That's what that would mean. So first, the notation. The notation for somebody being both a college degree holder and a voter is probability of A intersect B. And you can see where that vocab comes from. It's like the intersection of these two Venn diagrams. And so basically of these two circles here. And so basically A intersect B, that's that first vocab word that I said I'd introduce you to. Let me just make the colors match up here. So this is intersection. And really in English, the way to read this is the word and. And so this is the probability of A and B both happening, somebody college degree and voting, is this. Now, the neat thing here is I could then ask you about, well, sure, if that's the probability of somebody being both, what's the probability of either or? Meaning, what's the probability of A or B? So I'm going to use green because that is what we then refer to as the union. And so basically the union of two events is the likelihood of either one happening, A or B. So that's A or B, and that's union. Now, here, I basically don't need any additional information to find this. Basically, from the information I have, I could already find the probability of A or B, meaning the likelihood of throwing the dart somewhere in this 1 by 1 thing and it landing really anywhere here, anywhere in this green region, which is if you land either in A or B or the overlap, really, anywhere in there, what's that probability? That's really what this union thing is going after. What's the likelihood of A or B? Well, if we were the first people trying to come up with the formula, we might just think, all right, well, that's just basically, we'll just add them up, right? A and B, add them up. And that's definitely a part of it. So the formula actually for probability of A or B is equal to probability of A plus probability of B. That's part of it. But we can kind of already see if we just stopped there. I mean, for this problem, it's kind of obvious that that wouldn't work because 50% plus 60%, that's already more than 100%. That's 110%. So it can't just be that. And that's because you realize that if you do A, then you kind of don't want to, like, part of B, the overlap part, has already been counted in A. And so we only want this much additional. So we don't really want all of B. We basically want B minus that intersection part. And so long story short, the actual formula is A plus B minus the intersection A and B. And it's not because we don't want to include this. It's just that we don't want to include it twice, because the intersection is kind of a part of both of these. And if we add them, then we're going to have double counted it. So subtracting just makes sure that we don't double count it. So applying that formula here, the probability of somebody having voted or gone to college is, let's see, 50% for college, 60% voting, minus 30% overlap. And so that overall will be 0.8. So there's an 80% chance of basically being in this green region, meaning either having voted or having gone to college. And notice that if this green is 0.8, if that's 80%, well, and if the whole thing is 100%, well, then you can also figure out that the probability of being neither a voter nor a college degree holder must be 20%, because essentially 80% plus what is 100, so 20%. So you could also do that if you want. That basically the probability of, neither is 1 minus the probability of either, meaning A or B. But in either case, so we've talked about intersection and union. Now let's talk about conditional probability. So now in this example, what if I ask you the following? What's the probability of A given B? So first of all, that's the notation here. Anytime you have this vertical bar separating the two events, A and B, the way to read that, first of all, is, and I'll make this color red just to match. This is A given B. So in this context, A being college, B being voted, this is basically, to translate it, going to say the probability of, so it's still ultimately, it's still P of A. So it's still the probability of college given that they voted. So this is saying that suppose you basically pick someone that you know for a fact is a voter. You know for a fact that they voted, and now you're wondering what's the likelihood of them having a college degree. That's really what you're after here. If you were asked P of B given A, like the other way around, that would mean suppose you have somebody who you know for a fact is in college or has a college degree, what's the probability that they vote? So basically here, the order matters here. A given B and B given A are very different things. So really it's just important to start with the given part, the second one, and then it's ultimately still asking for P of A. So in this case, the formula is this. I'll first tell you the formula, and then we'll see where it comes from. So the formula of A given B is the probability of A intersect B over the probability of B. Now, if we were the first people trying to come up with this formula, what would kind of make sense? So instead of asking ourselves just P of A, like what's the probability of somebody going to college, we're kind of asking ourselves, here, I'll erase this for now. We're kind of asking ourselves, what's the probability of somebody going to college, but given that they've voted, right? So it's instead of the denominator being this whole board and asking ourselves, what's the likelihood of a randomly thrown dart being somewhere in A? we're really asking, what if the dart has already landed? The dart has already landed. It's been thrown randomly. It's already landed for a fact somewhere in B, but we're wondering what's the chances that it also was in A? Well, again, if it was truly randomly thrown, then the overlap probability divided by the total is going to be our answer. Because really the only chance you have of being in A is the overlap. Because otherwise, like this doesn't count because this is not in B, right? Because the dart's already been thrown. It's already landed for a fact somewhere in B. And we're now wondering what's the likelihood of it also being in A? Well, that's just the overlap region. That's the only possibility remaining for it to have been in A, divided by out of this much total probability, right? So out of this much total, this guy. So if we were making up the formula, it's whatever this area is, this 0.3, but really P of A intersect B, or 0.3, divided by out of this much total space, 0.6 we said, so or P of B. So that's sort of where this comes from. It's like this much out of this much. That's the likelihood of A given B. So in this case, that would be, let's see. So in this case, if we were to apply that here, that would be 0.3, because that was the overlap. This equals 0.3 over 0.6. So basically here we have that basically simplifies to 0.5. And so that's our conditional probability. Essentially, there's a 50% chance of somebody having gone to college given that they voted. Now, here's the thing. This is where we could now define what it means for two events to be independent. Here, notice that when I asked you, like in general at the beginning, like what's the probability of somebody going to college? Well, without any information, it was just 50%. Now here, this is basically asking you the same question. It's what's the likelihood of somebody going to college? But here you're given this additional information, which is that they voted, and that still ended up being 50%. Now, this actually, believe it or not, is a coincidence. And when that happens, when basically the probability doesn't change, when the probability of A is the same, whether or not this B is given, that is a sign that the two events are independent. So basically, we could kind of define it this way. First, so there's a few ways we could think about this, but first we'll say independent events. So two events are independent if the probability of A given B is simply just equal to the probability of A. So if this is true, this is an implication of two events being independent. So if it's independent, then we know that this probability will be, I'll just put it this way. So if it's independent, then we know this will be true about them. Now, in this example, what if literally I just changed this overlap? Like, let's say we just did a different problem where the overlap was slightly bigger. Like literally, what if I kept everything the same about this? This is still 50%. This is still 60%. But what if in the beginning I just said this is 40%? That's totally plausible. You could imagine that having been the case. Like if this was just, this event A over here is 50% area, event B over here is 60% area, and the overlap here is 0.4. Well, now the probability of A given B is 0.4 over 0.6, which is basically 2/3. So that simplifies to 0.666. And so now it's kind of like, all right, in general, the likelihood of going to college, P of A, was 0.5. But given this information that you're a voter, now your probability of it's kind of been upgraded a little bit. When we were given some information, we kind of updated our minds about what P of A was. Instead of just 50% for a randomly selected person, if I know that you're a voter, now there's a little bit more than 50%. Now there's a 66% chance that you've gone to college. So that means that the two events are in fact not independent from each other, right? So basically that's really how we can use conditional probability. Now, another way to think about independent events is looking at this, like what if, just to not to get too into like the theory and deriving things, but the formula for A given B is simply like, let's say we take this and just try to rewrite it a little bit. A given B we know is A intersect B divided by B, right? That's just from earlier, the overlap over B. That's what this was. And we're claiming that two events are independent if that equals just the straight up probability of A. If you simply multiply P of B to both sides, this simplifies. So if you just multiply P of B to both sides, the left-hand side, just this cancels and you just get P of A intersect B. And on the right-hand side, this just becomes P of A times P of B. And now we have a new way to think about what it means for two events to be independent. It means that the likelihood of their overlap, the likelihood of both of them happening, is simply their product. Basically, the likelihood of, in this case, college and voting, if they're truly independent, then that means that their overlap must simply be their product. Now, this is something we see all the time. Like if we ask something like, what's the probability of, say, getting two heads in a row? Well, if the two flips are completely independent, then the probability of basically both of them being heads, like the intersection, is simply just you multiply them. So whenever you have two events that are independent, to find the probability of them jointly happening, the intersection, you just multiply their probabilities with each other. So in the heads or tails example, it's just 0.5 multiplied by 0.5. So that's how you could think about two events that are independent. Finally, just because a lot of people confuse independent with what's called mutually exclusive. So a lot of times people think, all right, independent and mutually exclusive, maybe they're like, kind of like, all right, the same thing, like mutually exclusive, independent. But it's actually kind of like the opposite, because mutually exclusive simply means, so mutually exclusive just means that there's no overlap at all. There's 0% chance of both happening. That's basically saying that the probability of A intersect B is 0. So if for two events, it's like A and B, like no overlap at all, that's what it means for them to be mutually exclusive. But then it turns out if it's mutually exclusive, then they're definitely not independent from each other, because if they were independent, then like this would be true. Then A given B would be A, versus here, if they're mutually exclusive, then probability of A given B would be 0. So if they're mutually exclusive, well then basically the probability of A given B would simply be 0, because keep in mind, probability of A given B was the overlap, because the formula is the overlap over B, right? So the overlap divided by P of B. But the overlap, there is nothing. So if the dart's already been thrown and landed in B, the chances of it also having landed in A is 0, because if it's already in B somewhere, but there's no overlap for it to also be in A. So if two events are mutually exclusive, then if one's happened, conditional on one happening, the other's probability is 0, which is, obviously that's not equal to P of A. And so that means that they can't have been independent from each other. They're in fact very related to each other. If one happening, there's a dependence relationship, because if one happens, the other cannot, meaning information about one gives you information about the other, versus if they're independent, knowing something about one gives you no information about the other.